Welcome students. Our today lecture is on asymptotic notation. So these are the contents of our today lectures: introduction to asymptotic notations, types of the asymptotic notation, determining the time complexity of a simple algorithm, introduction to, to an algorithm, memory address calculation in one-dimensional array, and reading and writings in one-dimensional array. Now, asymptotic notations. Asymptotic notation is a method of defining the mathematical foundations of algorithm runtime performance. In other words, asymptotic notations are the expressions that are used to represent the complexity of an algorithm. So, we use generally interesting in order of growth of running time of an algorithm, not in exact running time. This is also referred to as the asymptotic notation. So, in short and sweet, we can say that asymptotic notations is basically used to calculate the performance of an algorithm. The asymptotic notations give us a method of classifying functions according to their rate of growing. Now, there are basically three types of asymptotic notation: big O notations, big omega notation, and big theta notation. Now, we consider here the definition of big O notations. Here, we mention the mathematical notations or mathematical definition of big O notation. Here, we consider fn is a function that is considered like as a omega big O notation of Gn if there are two positive constants C and N0 in such that mod of Fn less than equals to C of Gn for every value of n greater than equals to N0. If Fn is not negative, we can simplify the last condition to the value of this is such a way Fn greater than equals to 0 and Cgn greater than equals to Fn for all values of n greater than equals to n naught. So, we can say that Fn is big O of Gn as n increase the Fn grows no faster than Gn. In the other words, Gn is an asymptotic upper bound of Fn. So, here we consider here graphical notation here, that is the denote this point denotes the F naught required condition, and here Fn grow the faster than Gn, and we can say that Gn is the constant multiply of C, and he always denote the upper bound. Now, here we consider the example for understanding the big O notations. Consider here there is two function fn and gn. So, fn function is defined 3n plus 2, fn equals to 3n plus 2 and gn equals to n. Now, according to the definitions of fn as big O notation of gn, we satisfy these conditions. Fn should always less than equals to constant multiply of Gn for all values of C greater than 0 and n greater than equals to 1, and Fn less than equals to C means constant multiply of Gn. So, using this condition we apply here 3n plus 2 less than equals to C n. So, considering this inequality, we observe that value of C equals to 4, these conditions satisfy, and here n should be greater than equals to 2. So, there are two parameters C and n. Value of C equals to 4 and value of n greater than equals to 2, these conditions fully satisfied. So we can say that Fn 3n plus 2 is a notation of n. In other words, Fn is a big notation of Gn. So we can say Gn is a asymptotic upper bound for of on Fn. Now, next is big omega notations. So, there is the mathematical definition of big omega notations. Here, Fn is equals to big O notation of Gn if there are two positive constants C and C naught. If Fn greater than equals to C constant multiply of Gn for all values of n greater than equals to n naught. If Fn is non-negative, we can simplify the last condition in such a way that Cgn greater than equals to 0 or Fn greater than equals to Cn for all values of n greater than equals to n naught. So, we can say that Fn is omega of Gn. As n increase, the Fn's grow no slower than Gn. So, in other words, we can say that Gn is an asymptotic lower bound of Gn. So, using the graphical notation we consider here this Cgn is denote the lower bound and it is used to determine the lower bound of this Gn function, and Fn is goes after a constant values of n naught is always get higher than the Cn. Now, example of big omega notation, we again consider the same example. Fn value is determined here, is given here 3n plus 2 and Gn value is n. So, according to the condition of big omega notation, we apply here Fn greater than equals to C of Gn for all values of C greater than 0 and n not greater than equals to 1. So, according to the definition, Fn should greater than equals to constant multiply of Gn. So, we put the value of Fn and Gn here. So, Fn value is here 3n plus 2 and Gn value is n. So, that is the constant multiply of C. So, now we solve this inequality using the values of C and not here. Above condition is true for all values of C equals to 1 and n greater than equals to 1. So, by using the big omega notations, we can represent the time complexity as below. F3n plus 2 is omega notation of n. So, we can say the building block of this. Now, next is the big theta notation. According to a definition of the big theta notation, we mention here Fn is theta notation of Gn if there are three positive constants C1, C2 and n naught such that C1 multiply of Gn less than equals to Fn and C2 multiply Gn greater than equals to Fn. So, in other words, the value of this Fn function is between two constant multipliers C1Gn and C2Gn. So, according to definition, if Fn is non-negative, we can simplify the last condition as mentioned here. Value of C1Gn greater than equals to 0 and Cngn should be less than equals to Fn and Fn should less than equals to C2 of Gn for all values of n greater than equals to n naught. So, we can say that Fn is theta of Gn, and as n increase, the Fn grows at the same rate of Gn. So, that is considered as a big theta notation. Now, in other words, Gn is a asymptotic tight bound for Fn. Now, that is the graphical notation. Here, Fn gets its value between C1 Gn and C2 Gn. That is the representation of graphical notation. Now, here we take a mathematical example for explain the big theta notation. Here we taking Fn equals to 3n plus 2 and Gn equals to n. Now, according to the definition of big theta notations, we have to follow the given conditions. If we want to represent Fn as theta notation of Gn, then it must satisfy these conditions. C1 Gn less than equals to Fn and Fn less than equals to C2 of Gn for all values of C greater than 0, C1 greater than 0, C2 greater than 0 and n not greater than equals to 1. So, according to this condition, we apply to prove the big theta notation here. C1 n less than equals to 3n plus 2 less than equals to C2n. Now, above condition is always true for value of C1 equals to 1, C2 equals to 4 and n greater than equals to 2. So, by using this big theta notation, we can represent the time complexity of any algorithm. So, we can say 3n plus 2 is the order of n or theta notation of this n. Now, next point is determinations the time complexity of a simple algorithm. Basically, these notations are used to uh, provide the performance of an algorithm, and basically any algorithm is determined by the time complexity. Any algorithm performance is determined by the time complexity and space complexity. So, we will consider here the time complexity of this simplest algorithm. Here we are taking and simple coding for count now the number of values. So, here we basically use count starting 0 and we apply a loop. This loop is known as a outer for loop, and we use an inner for loop for get the increment in the value of the count. So, here we take when I 0 it will return 0 time, when I 1 it will runs 1 time. So, this is the frequency of running this algorithm. At I equals to 0, it will returns 0 time, 1 time and 2. So, we can say that it basically follow a simple pattern of 0, 1, 2 and so on. So, the using the mathematical formula, we calculate the basic form of sum of 0 to n minus 1 equals to n multiply n minus 1 by 2. So, we can say that the complexity of this algorithm is order of n. Now, our next topic is array. So, what is the array? An array is basically a data structure that contains group of element. Typically, these elements are all of the same data type. An array is collection of similar data type and basically are used to store a continuous memory locations with a single name. An array is a special type of the variable used to store multiple values of the same data type at a time. Now, here is syntax of representing a one-dimensional array. When we want to declare any one-dimensional array, then that is the simple way or simple syntax of declaring a single dimensional array. First we have to mention data type, then array name, then size of array. So for example, I want to declare a array of 10 elements and I want to store all elements of the same data type like as an integer. So I have to mention data type for this array is like as an int, and the name of array I give here AR, and size is mentioned in this parenthesis like in these brackets like 10. So declaring this statement, there will allocate a memory for array name AR of 10 bytes. So that is the way of declaring the one dimensional array. The syntax for creating a one dimensional array with size and initial values. This is the another way of representing. So if we want to initialize any array at the time of the declaring, then we have to use this syntax. First I have to mention data type, then array name, then we give the size of array, and here we mention the value which we want to allocate these elements. So that is the another way of declaring the array. For example, here I want to declare with size of 4 integer data elements, and I give these values here 2, 5, 1 and 4. That is the initializing syntax of one dimensional array. Now, why do we use one dimensional array? Basically, we know that when we use the number of the variable of same time, then before using the array we mostly use the variables like int a, int b, int c, and that is was the confusing way the how many number of variables we have declared, and this task was basically very complicated. So to remove this problem we basically use the array. The compiler allocate for above mentioned statements 2 byte memory with name A, same 2 byte for name B, and another 2 byte for name C. So these 2 bytes will be allocated different memory location. Not so at the time of the compiling we have to pass the different memory locations, but using the array they always use the consecutive memory. Now, for example, we consider here for this is value for A, this B and this C. So, these values are not allocated the consecutive, they are allocated at the different memory locations. So, at the time of the compiling, we have to link these data at the execution during the execution time. So, that is the time consuming task. So, here the memory is organized as shown in the figure. Assume that each box is 2 byte for memory. So, A will take 2 byte, B will take 2 byte, C will take 2 byte. And using these variable, their corresponding allocate value will connected. Now, why do we use an array? Now we consider here declaration int a30, int a3. So when we declare this statement, then there will be allocated memory in such a way a0, a1 and a2. These are known as the subscripts of this array, and array is basically address is always allocated with the 0 and so on. And here this denote the index of an array 0, 1 and so on. The compiler allocate total 6 byte for continuous memory allocate with the single name A, but allow to store 3 different integer values each in 2 byte of memory at a time, and memory is organized as mentioned here. Now, our next topic is memory address calculation in one-dimensional array. So, when we declare the one-dimensional array, then we always have to consider two things. First one is address and second one is indexing form. Basically, index is always start 0, 1, 2, 3 and address, if there is no any address is mentioned, then by default we consider 0, and the starting address index of an array is known as a lower bound and last index of array is always known as a upper bound. So, here lower bound is 0 and upper bound is 5, and the starting address of element is known as a base address, and the difference between two consecutive memory addresses is known as a width of element. So, using these things we calculate the address of a specific script of a one dimensional array in such a way A of I denote basically index or script of a specific element equals to B plus W into I minus LB. Here B is basically denote the base address and W is denote the byte consumed by the element. If there is integer, then he will take 2 byte. If it is character, then it will take 1 byte. And I denote the index or specific script where we want to calculate the address, and LB denote basically lower bound. So, that is the general formula for calculating the memory address of a specific element in one dimensional array. Now, next topic is reading and writing in one dimensional array. As we know that array is basically consume a consecutive memory allocations. So, when we giving input and we are taking output, it means we are reading or writing, then we always have to use the for loop. So, using the for loop we have to read, and using the for loop we have to write. So, in the reading syntax we basically use for loop I equals to 0, I less than 4, I plus plus, and then we give the input functions. And similarly, because writing process is same like as a reading process, but we have to use here the output function. So, our today lecture is finished here. Thank you.